All right, so we're going to today continue our discussion about what happens when you try to do sound inside of a room, which, as when we were talking about acoustical gain last time, I hinted at. Because so far in our conversations about sound and how it works, we haven't really been thinking about things like microphones and rooms and what their impact might be on all of this. But of course they have an impact. So last time we talked about what impact does the microphone have on this, because as we learned, just because your sound system and your loudspeaker might be capable of delivering a certain amount of sound pressure level at the seats doesn't mean that you'll ever get to make that much sound, because the microphone might not allow you to do that, because you might start getting feedback before that happens. So now today what we're going to talk about is what happens when you introduce walls into this equation, because walls have an impact. So in other words, we're talking about acoustics. So today is our one single class that we're going to actually spend any formal time talking about acoustics. Acoustics is a big subject, and we are not going to be able to, in an hour and 20 minutes, get to the bottom of of everything that's related to acoustics. There are people that devote their entire lives to trying to understand that. But I'm going to hopefully give you the basics. And it's important for you to understand that we are not training you to be acousticians, okay? That's a whole other specialty. We're training you to be sound designers, and there's a difference. And so, but you do need to understand a little bit about acoustics, because it does affect the world that you live in and the world that you work in. So you need to understand a little bit of it, but just be super careful when you get out there into the big wide world, because not everyone understands that these are different things, that sound design and acoustics are different. They're not the same specialty. And you can very easily get sucked into an acoustics problem that you have no business getting involved in. We went through that a little bit on this Still Life with Rocket show that we're doing over at the old tobacco plant. There's some acoustics issues there. And, and I had to fight pretty hard to keep us and our students from getting sucked into solving that problem, because we can't. That's not what you guys are trained to do. And it's not even where my I don't have deep expertise in acoustics. And a lot of, I can't tell you how many times I've been sucked into that, or attempted to get sucked into that. Where you're doing a show in a space and you run into what you suspect is an acoustics issue, and everyone turns to you for information about how to solve it. And you have to be very careful about how you respond, because acoustics is essentially the study of what happens when sound runs into something. Okay? What happens when sound hits an object? That's the study of acoustics. And the most common object that sound hits when you're doing sound inside of buildings is walls. Okay, so the sound hits a wall. And so if you have an acoustics problem, it's because the walls are either in the wrong place, or they are pointed the wrong direction, or they don't exist where they ought to exist. And fixing those kind of problems is expensive and complicated, and usually not practical. And if you start making stuff up because you don't want to look stupid, and people start asking you about how do we solve this acoustics problem, and you start making stuff up, like telling people, oh, hang a bunch of curtains over here, or oh, put all the, spend $10,000 on these panels that I found on Sweetwater, and let's put them all over the ceiling. You are going to make someone spend a whole lot of money and time on something that is probably not going to solve the problem, because the problem is way more complicated than you can understand. Okay? And they're going to be very unhappy with you when you make them spend thousands and thousands of dollars, to solve a problem, and then that problem is not solved. because you were pretending to know things you don't know. Okay? So be super careful about that. They're going to be a heck of a lot more mad at you, when you make stuff up and they spend money and don't solve the problem, than they will be if you just are honest with them and say, you know what, this is really not my area of expertise. I'm not really qualified to advise you on this, right? They might be a little annoyed when you say that, but they will be a heck of a lot more annoyed if you pretend like you know what you're talking about and then screw it up, okay? So, that being said, just like in the rigging class that you guys take, we're not necessarily expecting that you guys will become expert riggers coming out of that class. But hopefully you can come out of that class at least knowing when something looks weird or suspicious or maybe not safe. Or being able to evaluate your own plan and go, does this seem reasonable or not reasonable? Should I get somebody else to look at this or should I not? That's really the goal. Same thing about acoustics here. I just want to get you guys far enough into this to be able to understand the basic kinds of problems you're going to run into, what the vocabulary is in the way you talk about this, so that you can spot these situations where you can maybe give a little bit of advice and then pass them on to someone who really knows what they're talking about. Okay, so I said acoustics is the study of what happens when sound runs into something. And there's really 4 things that could happen, and they're up here on the board. So a sound wave can run into an object, and we've already talked about this first one, right? It's possible that the sound could go around that object, depending on how large the object is relative to the wavelength of the sound that's hitting it, right? If the object is relatively small compared to that wavelength, the sound will just go around it very easily. Whereas if the object is very large relative to that wavelength, it'll be harder for the sound to go around it, but it will get around it eventually as long as it's of a finite size, okay? Meaning, as long as the wall doesn't go on forever, eventually the sound will find a way to get around it, okay? And we know that. It's very, very difficult to make a perfectly soundproof room, right? The sound will get out, okay? But there's 3 other things that can happen. One is the sound could be reflected off of that surface. The idea being that you've got this energy that is coming in here from the room, hits the wall, and remember, sound is just air molecules vibrating, pushing against each other. So those air molecules just push against that wall, and they keep pushing and pushing and pushing, and eventually that energy builds up against that wall, and this is an elastic thing, so at some point that energy is going to bounce back, right? It can only push on that wall for so long before it's going to give up and start heading the other direction, okay? So there's some of that energy could be reflected, okay? Come back into the room. Some of the energy could be absorbed depending on what this object is made out of. As that air pressure starts pushing up against that wall or that surface, it might find a way to get through it. And if it can find a way to get through it, it's going to try to, okay? Because if it's easier to get through it than it is to bounce off it, then it's definitely going to do that. Okay, that energy is going to take the path of least resistance. Okay, so some of that energy could be absorbed, and if it gets absorbed, it just kind of stops there, right? Because it's easier to go through it than it is to bounce off of it, but it's still harder to go through it than if the object wasn't there at all, and therefore the energy is not going to transfer perfectly through that surface. Some of it's going to slow really, really well down as it goes through that. That's kind of what these panels do. Okay, these are, made of it's like fiberglass, when the sound hits this, this presents a little bit of resistance, but nowhere near the kind of resistance that the drywall does. So the sound is going to go in there, and the energy is just going to slow way down. And by the time it gets to this wall, then whatever's left definitely comes back, but it then has to go through this again. And by the time it comes back out, it's way, way, way lower energy than it was when it started, okay? So the third thing that can happen is some of the energy can be transmitted by the surface, okay? This is stock and trade for musical instruments, okay? So that's what, we were talking about the bass earlier. Like, that's what's happening, okay? Is you have energy that is being transmitted by that piece of wood that is vibrating, okay? So that energy is going through a couple of transformations. It starts as a vibrating string, and then that energy is transmitted through that bridge into the wood panel, and that wood panel is now vibrating the wood panel. And that wood panel now vibrates the air, and then you hear it, okay? So this surface, again, depending on what it's made out of, could become a whole new radiator or resonator. It can become the new thing that's making the sound, okay? This is usually if the walls are very thin and don't have a whole lot of supports in them. It can vibrate kind of like a drum, okay? And that new surface becomes the new sound, okay? Just because it's vibrating because of the air that's pushing on it, right? That air hits it, pushes on it, and it starts vibrating like the air was vibrating, and it re-excites the air on the other side of the wall, okay? That can happen. Now, in reality, all four of these things happen at the same time to some extent on every surface, okay? So the study of acoustics is really about what percentage of the energy is doing each of these things, right? How much of the energy is getting around the surface, how much of the energy is reflecting off the surface, how much is being absorbed, and how much is being transmitted. And depending on that ratio, it's going to have a different result, and that will affect then what you hear or don't hear in the room. Everybody with me so far? That being said, the two most common things that you deal with in acoustics are reflection and absorption. Okay? Most acousticians, they spend most of their time talking about that. They don't spend a whole lot of time talking about diffraction, which is what bending around, and the transmission. Because people hire acousticians not so much to stop the sound from getting through the walls. That's, people hire acousticians to figure out how to get the room, the people in the room to hear what they need to hear. They're not so concerned about what the people outside of the room are hearing or not hearing, okay? But sometimes they are. But usually, reflection and absorption. So this is the concepts of acoustics have been around for a long time. I mean, theater has been around for a long time, couple millennia. And, there are, outdoor amphitheaters from ancient Greece, where they were doing shows, and, it's a little unclear the extent to which they really understood the science of the acoustic science involved there, but they definitely figured out ways to get the acoustics to work for them and to their advantage. Whether or not they may have understood it really well, and they just used different language to talk about it than we do now. But at any rate, those concepts have been around. Acoustics, sound has been behaving the same way for a very long time. However, it's only been really in the last 100 years or so that we've started to develop the science and the language of the science to be able to talk about it in some sort of universal way. So that's what I want to talk about now is how do we talk about this and measure it and predict it and calculate it. One of the most famous scientists that did some of the really kind of influential research into acoustics was this person named Sabin. Okay, Mr. Sabin. Okay, and like every good scientist, named his own discoveries after himself. Okay, so if you've ever heard the word Sabin getting thrown around in the context of acoustics, this is a person's name, the name of a person who thought about this a little bit, or a lot actually, and tried to come up with some ways. And what Sabin observed was that he wanted to figure out a way to measure reflection and absorption, and to talk about it in some way that was consistent. And so he essentially invented a unit of measurement, okay, which is really kind of cool. This is a really smart person. He invented his own unit of measurement, and the unit of measurement involved absorption. How much absorption? And he said, well, how could we measure this? How could we measure sound absorption? And he said, well, any unit of measurement has got to have some sort of limits, right? some sort of agreed upon starting point. In the metric system, it's a meter. Apparently, there is actually a metal rod, I think somewhere in France, locked in a room that is officially 1 meter. Like that is, someone said, this metal rod that is this tall, that is a meter. And then everything, the entire metric system was built around how much larger or smaller something was than this metal rod. And that thing, you can look this up, it exists. It sits somewhere, I'm sure in a museum somewhere now. So he was trying to do the same thing for absorption. He said, okay, well, what would be the thing that we could measure everything against? And he said, well, what would be, if we're talking about percentages of reflection versus absorption, he's like, I don't know what a perfect reflector would be. What would 100% reflection be? I don't know what that would look like or what sort of material that would be. But I could imagine what 100% absorption was like. And that would be sound going up against some surface in a room and none of it comes back at all. And if we could start from there and then measure everything relative to that, then we might have something. So he was thinking, well, what is the thing that is a perfect absorber acoustically? And he said, well, I tell you, it's an open window. So if, you've got this room, for example, and there's the door, and we've got the door open right now, any sound that hits that part of the wall is not coming back. Okay? It's going to go through that part of the wall, and we don't ever get to hear that again. Okay? So this was his grand conceit, was we're going to say that the perfect absorber is an open window. So that's 100% absorption. And then we're going to imagine some sort of unobtainium that is perfect reflection. And it doesn't really matter what that is, what we can imagine that it might exist, and it would be equivalent to 0% of open window. Right? So then his unit of measurement that he came up with was, he said, okay, 1 Sabin is going to be equal to 1 square foot of open window. So if you can imagine the total surface area of some object, 1 Sabin would mean that 1 square foot of that total area would be open window. That would be 1 Sabin. Okay, and if the whole thing was open window, then it would be whatever number of Sabins would cover that entire surface. Right? So if it was a 10-foot by 10-foot wall that was perfect absorber, how many Sabins would that be? Probably 100 Sabins, right? Because there would be 100 square feet on that. So you would call that wall 100 Sabins. Okay? So, okay, how does that help us? Well, what happens is, if you can think about, so let's say you've got a surface that has whatever absorptive qualities it has, but let's say that its absorption coefficient of 0.1, which means it absorbs 10% of the acoustic energy that hits it. Okay? So sound hits this surface, and 10% of that energy gets absorbed. Okay? Which means that the other 90% of it probably gets reflected. Okay? So and let's say that you had 100 square feet of this material. So this same 10-foot by 10-foot wall was made of a material that absorbed 10% of the acoustic energy that hits it. Okay? Well, you could call that wall, that 100 square foot wall, is equivalent to 10 Sabins. Because that 100 square foot surface absorbs energy at the same rate as 10 square feet of open window would. Okay, you with me so far? It's a little bit kind of a kooky idea, but it worked for a good long while. Okay, but there was a problem with that. Can anyone spot it? What is the problem with this invention he's come up with? Remember, I said he invented a unit of measurement called the Sabin. What is the problem with this new unit of measurement? You could, you could. You could use a sound pressure level meter and measure how much is coming off. So you could do that.
Would it be because it's measuring how ineffective something is instead of how effective it is?
Well,
measuring how something isn't acoustically successful.
Well, so you're making a value judgment there, right? Is it better that the energy get absorbed or reflected? And the answer is it depends, right?
Is it because, that says that it's equal to 1 square foot.
Yeah.
But is it because you have to do a bunch of math to actually figure out how many Sabins it actually is?
So you're getting close. So the issue here is that you've got a unit of measurement that relies on another unit of measurement. Okay? So what if you're somewhere where, they don't measure things in feet and you measure things in meters? Then how do you figure out how many Sabins it is? Because a Sabin is defined as 1 square foot of open window. Like that is the definition of 1 Sabin. So that becomes a little bit of a problem because strictly speaking, unless you're measuring surface area in feet, trying to figure out what the Sabin is going to be a little bit tricky because the Sabin is defined in square feet. So that's kind of a little bit of a problem that we ran into over the years. But the concept was really good. Okay, the concept of, how could we kind of start measuring and calculating this stuff? This is a great start. Okay, but now we don't so much talk about Sabins anymore because of this weakness in what he sort of did, because he's sort of creating a unit of measurement that relies on another unit of measurement in a very specific way, and that's kind of our problem. So instead, we start talking about, we just start talking about it in terms of absorption coefficients. So instead of, Sabins and open windows and everything, it doesn't really matter anymore. We don't really care. We just call that perfect absorption a similar unobtainium as the perfect reflector. And we start looking and talking about surfaces in absorption coefficients, which means, like what is the percentage of energy that gets absorbed? So I mentioned it earlier. So you could if something had an absorption coefficient of 0.1, that means 10% of the acoustic energy that hits that surface gets sucked up by it, whereas 90% of it would be reflected. So we would just talk about that material as it has an absorption coefficient of 0.1. And so this way we don't have to tie it to any particular unit of measurement. We can use absorption coefficients in any unit of measurement, right? Whether it's feet or metric or whatever else you could come up with. So let me give you an example of how this might work. If you can talk about absorption coefficients, then you can talk about the entire room and figure out an average absorption coefficient for the whole room. If you look at the absorption coefficients of all the surface area in the room, you can say this room in total has an absorption coefficient of this much, which means 20% of the energy that hits the surfaces in this room gets absorbed, and 80% of it comes back. Okay, and that's helpful to know. This also then allows you to calculate dB loss, right? Because if you know that a certain number of percentage of this sound doesn't come back, then you could do the math to figure out how many dB quieter it would be coming back at you based on that coefficient. So let's say you had a room that has, well, we'll do this in meters just to prove the point. It had a total of 1,000 square meters of total surface area. And I'm talking about the floor, the ceiling, and the walls. So you add all that surface area together, and it's 1,000 square meters. So make sure I bring this with me. So let's say you had, so 200 square meters of this material is some sort of stuff that has an absorption coefficient of 0.8. Okay, and the other 800 square meters has an absorption coefficient of 0.1. So that means for 200 square meters of surface area in this room, 80% of that energy gets absorbed on that material. But for the other 800 square meters of surface material, 10% of that energy gets absorbed, and the rest of it comes back. Okay? So what could you do with that? Well, if you just took this 200 square meters and multiply it by that absorption coefficient, so 200 times 0.8, that's going to equal 160. Now, some people will call that Sabins. But I don't really like that, just because technically Sabins is square feet. But that is 100. It is equivalent to 160 square meters of perfect absorption. Right? But again, some people will still use the word Sabins. So 200 square meters of stuff that has an absorption coefficient of 0.8 is acoustically equivalent to 160 square meters of perfect absorptive material. Okay? And you could do the same thing down here. So 800 square meters times the 0.1 absorption coefficient would get you 80 square meters of perfect absorption. Okay? So you have a total here of, if you add these numbers together, what do you get? 240 square meters of perfect absorption. Okay? And again, some people would call that Sabins. So you could say this room is equivalent to 240 Sabins. Then what you could do is you could take that number, that 240 square meters of perfect absorption, divide it by the 1,000 square meters of total surface area in the room, and what do you get? What's 240 divided by 1,000?
0.24.
Yeah, 0.24. And what is that number now?
Your average absorption.
Yes, that is your average absorption coefficient of this room, which means generally for this room, 24% of the energy that, the acoustic energy that happens inside that room, 24% of it gets absorbed at the surfaces and doesn't come back. And the rest of it, with the other 76%, comes back. Okay? So that's kind of interesting. So what could you do with that? Well, let's round that to 0.2, just because it'll make the math a little bit easier. Well, what if you've got 0.2% of, or if you've got 2%, 20% of the energy getting absorbed, how much is getting reflected? All right, so that means that this room has an average reflection coefficient of 0.8. Right? If the absorption coefficient is 0.2, the reflection coefficient would be 0.8. So what would be 10 times the log of 0.8? That's what I got. Anyone else get that? So what that means is in this room, the sound comes back at you 1 dB quieter. Excluding issues of inverse square law, right? But the sound comes off of the surfaces of this room 1 dB quieter than it did when it hit the surfaces in this room. Okay? That's not a whole lot. This is going to be a fairly reflective room. Yeah?
I have no idea where you got that 0.8 and 0.1 from 200.
I just made that up.
Oh, you did? Okay.
I'm just saying that whatever this is, this is the drywall. You've got 200 square meters of drywall, and it has an absorption coefficient of 0.8.
Okay.
Actually, these would be curtains. So 200 square meters of curtains has an absorption coefficient of 0.8, and you got 800 square meters of drywall that has an absorption coefficient of 0.1.
Okay.
Right? That was where we started from. Okay, and then we just worked that up to figuring out that in this room, sound comes back off the walls in this room on average 1 dB quieter. Okay, so that's somewhat useful information. Yeah. So, any other questions about that? All right. So here's something I want you to look at. This is a little chart showing you the absorption coefficients at various frequencies for various types of materials. So I want you to stare at that for a moment and tell me what, if anything, looks interesting to you. Anything about that information make you go, huh?
The difference between a concrete block makes it
That's interesting, right?
very substantial.
So what do you suppose that's all about?
Paints
What does the paint do that makes it so much less absorptive?
it makes it, there's no like crevices.
Yeah, there's like no holes, right? It seals all the holes, and the holes are the thing that might let the sound through. Okay, so yeah, it makes a huge difference. Good.
What is that?
I think that's like
Is it like
I think
rolling?
yeah, I think that's like the sort of like wire mesh with the wood slats that they would. I think that's what that is.
So I would expect it to like keep going.
Say that again.
I would expect it to keep going higher and higher.
What do you start over?
I don't remember where I started. I would expect the like numbers to scale linearly.
Ah.
If it doesn't, it kind of drops off.
So you're noticing that you're basically noticing that different frequencies are absorbed differently, right? And maybe not the way you thought they would. Okay. So yes, that is interesting.
So like, but like some of them, like the concrete block, unpainted, starts at 0.36 and then moves. Well, actually, never mind. They're kind of all over. There's no just like starts at 0.36 goes down to 0.25.
Yeah, it's not a linear progression, and there doesn't seem to be a whole lot of rhyme or reason to how this changes. I mean, if you did the research and figure, you'd realize what it was. This is all relative to wavelengths and things, so that's all part of it. But yes, just like everything, all of the things that we talk about it depends, and the frequency. The absorption coefficient is different per frequency, sometimes dramatically different per frequency. The same material might absorb a certain amount of energy at a low frequency, but absorb a whole lot less energy at a high frequency. Okay, and we can talk a little bit about the science of why that is, but yes, that's an interesting observation, isn't it? That's something that we have to keep in mind. Because back to the conversation about average absorption coefficient of a room, what frequency was that? We didn't talk about that. What else? Anybody else notice anything that kind of makes you go, huh?
Wait, the Winger absorption tile.
Yeah, what is going on there? When it says look at 500 hertz on that absorption tile, and it says 1.23. What does that mean?
It's 123% absorbed.
It absorbs 123% of the energy that's thrown at it. How in the world does that work? How can it absorb more than everything?
It makes it louder inside itself and absorbs that too.
So let me show you what this thing is. This is the acoustic panel in question. So stare at that for a minute and see if you can guess, given what we've learned about how absorption coefficients are calculated, see if you can figure out what is it about that thing that makes it absorb more than everything. Say again? Interesting. You're very close. Yeah, you're very close. So yes, this thing has some thickness to it, right? So Keep thinking, because you're very close. You're so close. You're on the right track. But yes, the thickness of it has everything to do with why this thing is better than perfect. Again, go back and remember, how did we calculate the absorption coefficients?
Is it because it's oh, it's worth more Sabins than its actual.
Yes. Okay. So you got it. So think about, you're going to stick this thing to a wall, right? And it's going to cover a certain amount of surface area on that wall. Yeah? So that's however big that is. What is that? 3 feet? So how many square feet is this? 9 square feet. So it covers 9 square feet of surface area, but it introduces more than 9 square feet of total absorptive surface area into the room. Because it's got the sides. Okay? Here's the thing. That's hogwash. Okay? That's stupid. That is a very clever marketing person who is trying to make this thing look better than it really is. You could say, well, if you look at this just right, you could say that it is a 1.23 absorption coefficient because it introduces more absorptive surface area than it covers up, than it replaces, right? Because if you add up the surface area of the edges of this thing, it's 23% more surface area than is on the front, okay? So that's really stupid, okay? And actually nobody believes that. Nobody who knows anything about acoustics believes that. Every acoustician I've ever talked to that ever does it, they just say, yeah, we just call it an absorption coefficient of 1. We don't count the extra that the marketing people put on because it's stupid.
It's the random church sound guy who has to make his auditorium look like
Yeah, so yeah, if you don't know what you're talking about and you look and see this, you're going, ooh, I want that one. That one's better.
Well, we don't link to the other ones. That one's higher.
Yeah, it's like way better, right? So it absorbs a whole lot of energy. So go walk in front of that thing and talk into it. Stick your ear up against it. See how much sound comes back at you.
Ooh, that's weird. You feel like you go deaf.
Yeah. I mean, I'm not dissing this tile. It's actually a really great acoustic tile, right? It's just not quite as great as the marketing people would like us to believe. Just like talk into it, like count to 3 while you. like,
I don't like that.
like nothing comes back, right?
You should hear that, Nick? What?
Okay, so that's sort of interesting, right? So now here's my next sort of tricky question, okay? Why does it suddenly drop off, become less than perfect at 250 hertz and lower?
Because it goes around it. It goes around the size of the sound panel. So it's no longer completely absorbed.
Okay.
Through the window, if that makes sense.
You're so close. You're so close again,
Close a lot.
right?
Why don't we go back to once?
Well, okay, let me ask you. Okay, but why specifically 250 hertz and below?
Sound wave is huge.
Yeah, how big of a wavelength is 250 hertz?
4 feet. Well, it was 1,000.
4 feet, right? How big is that tile across?
You know, 3 feet.
We think about 3 feet, right? 1, 2, 3, 3 feet. Okay, so
Perfect.
I mean, ish, right? Close counts in sound. So, yeah, so 250 hertz is bigger than that tile, which means that tile cannot possibly perfectly absorb it because it is physically smaller than that sound. And we learned that when an object is smaller than the wavelength of the sound that's hitting it, some of that energy is going to go around it. Okay, so yeah, it can't possibly perfectly absorb it. And it gets even worse when you get down to 125, which is what wavelength? 8 feet, right? So something with an 8-foot wavelength is really going to go around that thing. Okay? So here's a couple of take-home messages about acoustic tiles. Okay, we put a bunch up in this room. What is interesting about these ones? Because they're basically the same thing. Okay? What do you notice about the way we put them up? Yeah, so that's interesting. We have these ones in the corners. What do you think that's about? Yeah, kinda.
Sound bounces off 2 walls and gets louder.
Yeah, we did learn about that. Yeah?
Can I ask, may I ask why the spacing is such?
Ah, yes, the spacing. What is the spacing about? Why did we space them apart? Well, in order, so let's say you believe this 1.23 to some extent. If you butt them up perfectly together, then you lose even that theoretical advantage. Right? So if there's no space between them, then you don't get to count the edges as surface area. You see why? Because that surface area is covered up. It's not exposed to the sound wave. Okay, so spacing them apart is super important. You don't want to just perfectly tile these things. Okay, the corners, that's an interesting thing. So these are called bass traps, and the idea here is that yes, we stacked them right, so they're taller. So that's a taller thing. That means a lower frequency is going to be able to be stuck in there. But there's also space behind there. Okay, and that space will help because even the energy that gets around that tile, it has somewhere to go, right? If it gets around it, it's going to get there behind it. And what happens when it gets behind it? What does it find there? Yeah, it finds 2 walls, and so it's going to reflect twice. And where's it going to go when it comes off of those 2 walls? Right back into the panel, right? And get sucked up again. Okay? So those corner pieces are really there to absorb lower frequencies because it introduces a larger surface area, and those lower frequencies that get around it are going to get stuck in that little cavity behind it and get absorbed a couple times. Okay? So it's a way of getting the same kind of tile to absorb a lower frequency than it would normally be able to do. Yeah.
Why do these panels, the side of them, have a little bit of an angle while that one is like 90 degrees?
Because it's designed to be a corner piece, right? They're trying to create so here's the extra ones we haven't used yet. So you can see this is a corner piece one, and this is a regular a surface piece one, just because they want to be able to flush mount it to the corner. Yeah, so that's interesting. And here's something I want you to look at. Given what I've just said, look at when I say acoustic tile, what I mean is the sort of white suspended ceiling tiles that used to be in this room and that are in a lot of other rooms on campus. That suspended ceiling has the white tiles with the lights in it. Okay, that's what this is. So there's 2 ways to deploy that kind of stuff. You can just glue it straight to the ceiling of the room, or you can suspend it down on wires and create that little grid and then pop them in there. And that's usually what people do, right? They suspend it down, and then there's that space above there. And most people think that's just because, well, then you can have that space to run wires and duct work and stuff like that, and no one has to see it. And yes, that's true, but that's not actually why you do it. You do it because it makes a huge difference in how much energy it is able to be absorbed by that tile. You see the difference between suspended and unsuspended? At 250 hertz, it's a massive difference. Why? For the same reason that the corner piece works, right? Is that if there's a volume of air behind it, then whatever sound gets through or around those tiles gets stuck in there, bounces off the ceiling, and gets absorbed again. Okay? So this is one of the few things I'll ever allow you to advise people on acoustically, is if someone tries to tell you that they're going to hang curtains on the walls of the theater in order to, quiet down the reflections. Happens a lot. A lot of people think that's a good idea. In some cases, it is a good idea. In some cases, it's not really going to help. But one little bit of advice I would give them is, if you're going to do that, you really ought to hang that curtain a little bit off of the wall, not right up against the wall. Because if you could hang it even just a few inches off of the wall, it'll be more effective at absorbing the energy you're trying to get. The other thing you could do, given what we learned about that tile, is rather than hanging that curtain and pulling it taut, why don't you ripple it a little bit? Accordion fold it. What would that do? That would introduce more absorptive surface area, right? So more of the curtain covers that same wall. And therefore, you could get theoretically more than, if whatever the capacity is of the absorptive coefficient is of that curtain, let's say it's a 0.5 absorption coefficient, well, if you ripple it and introduce 25% more total curtain surface area on there, then it effectively goes from being a 0.5 to a 0.75 absorption coefficient if you can just add more curtain by rippling it. Okay? Those are two little things that you are allowed to advise people on. Okay? Yeah?
So, we talked about okay, so in the tobacco warehouse or
Yeah.
factory, there is something that's happening where once you get, like 20 to 30 feet away from the sub, you just lose all of the low end. Like it's just not there anymore. Does that have to do with absorption, or is that something else?
That's probably just a room mode. It's a resonant frequency thing, like you're hitting the node, like we did that first kind of week of class. All right, so let's take a look at the next thing. So, okay, so that's what happens with the energy that gets absorbed. But what about the energy that gets reflected? What does that do? And this plays more into what you guys are experiencing over at the warehouse. Well, that sound that gets reflected, you hear that. Okay, because it hits the wall, it comes back and passes through your head. Okay, and therefore you get to hear that sound twice, right? Or maybe a million times, depending on how many surfaces there are in that room and how absorptive and reflective they are. You might hear that sound a lot of times, not just once or twice or 3 times. And if you hear it a lot of times, and those distinct reflections get close enough together, your ear-brain system has limited resolution, right? You can't. It's an amazing mechanism, our ear-brain system, but it has its weaknesses. And one of its weaknesses is it really has a hard time hearing the difference between two sounds that sound similar if they happen very close together in time. We do know that comb filtering becomes a part of that, right? But we don't necessarily, when you hear a comb filter because of a millisecond or two difference in two sounds, you're not hearing two sounds. You're just hearing one sound that seems a little weird, okay? So when these reflections get close enough together, and of course so imagine a million sounds combining slightly out of time with each other. The comb filtering gets so bad that your brain just rejects that as an error. It's like, okay, I'm just going to pretend that this is flat because this is such a mess, I can't even make sense out of it, okay? But it's going to think that that's all one sound, right? It's going to sound like one continuous sound. You're not going to hear the individual reflections anymore. That's what reverb is, okay? When you hear reverberation, that is the sound of millions of reflections that are just so darn close together that they sound like one long sound, okay? So if you've got a really reflective room like the warehouse, you're not hearing, if you yell and go, hey, it's not like you hear, hey, 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 right? You go, hey, and it sounds like, hey, right? Because what's happening there is that energy starts from you and it goes it hurtles towards all the walls at 1,000 feet per second in every direction. Okay? And once it hits those walls, some of that energy gets absorbed, but a whole lot of it gets reflected. And it bounces off that wall and hurtles at 1,000 feet per second in the opposite direction until it hits another wall. And a little bit of it gets absorbed, and the rest of it gets reflected, and it sends the other direction, 1,000 feet per second, until it hits another thing, over and over and over again. And every time that sound hits a surface, some of it gets absorbed, some of it gets reflected. Eventually, inverse square law takes over, because every time it travels through the air, it gets quieter as it's going, and every time it hits a surface, some of it gets absorbed, some of it comes back. And eventually, there won't be any left. Okay? And so what reverberation, when we talk about the reverberation time, that's how long does it take for that reflected sound to get to where we can't hear it anymore? If that's a really long amount of time, then that would be considered a very reverberant room. But if it's a very short amount of time, we would say that's a very non-reverberant room. So if we measured the total amount of energy in the room, which is what's happening on the vertical axis here, so you start making sound, and you keep feeding sound into the room until you get to the point where you are feeding the sound into the room at this exact same rate to which it is ultimately being absorbed. Right? So you can see that what's happening here, right, is this graph is eventually leveling out. And when it levels out, because you got time on the horizontal axis here, eventually you'll reach that point where the energy is getting absorbed just as quickly as it's being generated. Okay? And if you then cut off that noise source, the speaker, the loudspeaker, or the person talking, or whatever, you cut that off, and then you count how long it takes for that sound to go away and you don't hear it anymore. That's the reverberation time. We call that the RT60, reverberation time for 60 decibels. So how long does it take for that reflected energy to decay 60 decibels? RT60. And there's a lot of schools of thought about whether RT60 is really the right way to measure it. Some people say, hey, 60 dB, that's huge. I mean, once it drops 30 dB, you can't really hear it anymore. Think about your sound gym drills. When they do a 20 dB drop, that's a lot, right? Huge amount of energy that went away. Okay, so some people are saying maybe RT60 is too long because really the effective reverberation time is really just in that first 20 to 30 dB. So maybe we ought to just talk about it like that, and some people do. Okay, so the one thing that's really important to keep in mind here is to accurately measure that RT60. You've got to reach that point where the energy generation and absorption evens out, which is why something like a hand clap doesn't really tell you a whole lot about reverberation time. It tells you a little bit about how reflective the room is, right? You can get a sense of, okay, generally, does anything come back? Okay, kind of. But you're not going to be able to measure reverberation time off a hand clap, usually. Usually you need a little bit more. Now, if you're trying to do is figure out individual reflections, then a hand clap might help you. But to do reverberation time, you usually need a little chunk of time. Not a lot of time, but enough for that energy to even out. Yeah?
So if you're using like a reverb plug-in on a console,
Yeah.
and it says the decay time, and you put 3 seconds, is that using this
Yeah.
method of it'll be 60 dB down in 3
Usually.
seconds? So is that why it a lot of times doesn't feel like it's 3 seconds
Yeah.
long?
Yeah. Yeah, because really at about half that time is when you stop hearing it. Okay? Okay, so there's another type of reflected sound, though, that we call the early reflections. And the early reflections are the reflections that you hear after they've only bounced off one surface, or maybe two. But at that point, the reflections aren't close enough together for you to glom them all together as one sound. You can kind of get a sense that they are individual sounds. So here's an example where you've got a talker up here and a listener over here in the seat, and there will always be, hopefully, a certain amount of direct sound. We call this the direct sound that comes straight from the source to the listener without having bounced off of anything. Okay? And if we kind of figured this out, we would realize that what path could the sound travel that would be the next shortest path? And it would be this one. So that sound that hits here and reflects. That's the shortest, the first shortest pass. That'd be the first reflection that that listener would hear. The second one would be the one that goes off the upstage wall. That's the next shortest path that then gets to them. And then the next one would be this one. And then the next one would be the one that goes off the back wall and comes back. And there would probably be one, I don't have the floor in here, but the floor would probably be the second or third one, actually, if we counted the floor. But sometimes you can't count the floor if it's full of people. Okay? And then there's this other one. There is a path that could bounce there and then off the back wall and then get there. So depending on the size of this room, you might actually perceive these as individual sounds. Okay? So if those walls were really far away and there was at least a 30 millisecond difference between the direct sound and that first reflection, you'd hear it twice. That would sound like an echo to you if it's more than 30 milliseconds. If it's less than 30 milliseconds, that's when it starts comb filtering and you start thinking it's just weird, okay? That it's just one whole sound, okay? So, but here's the cool thing about the early reflections is if you start hearing double at 30 milliseconds, and we know it comb filters at 1 millisecond because we've heard that, but at some point, as you start increasing the time between the two sounds, that comb filtering gets so bad that you stop hearing it. That's called the critical bandwidth. And what that means is that eventually the cancellations and reinforcements in that comb filter get close enough together, just like when the reflections get close enough together, you hear it as one sound. When the cancellations and reinforcements in the comb filter get close enough together, you stop perceiving them individually as well. And that starts sounding like one continuous sound. So you don't hear the frequency artifacts anymore. That usually happens around 5 milliseconds. So you could hear two sounds 5 milliseconds apart, and at that point, you're not going to perceive the comb filtering anymore. So between about 5 milliseconds and 30 milliseconds, it just sounds like one sound, even though you're hearing it twice. Much more than 30 milliseconds, and you'll start hearing double. Much less than 5 milliseconds, and it's going to sound comb filtered. Okay? This is where the real meat of acoustics comes in. Because guess what? If you could get this first reflection, this R1, this reflection, if you could get that path, if you could angle that surface and arrange the people in such a way so that that reflection hit the listener within 5 to 30 milliseconds after the direct sound, guess what? The listener hears both sounds as though they were one sound. And it doesn't sound comb filtered. But what happens when two sounds combine together in the air and they don't comb filter? What is the other result? They get louder, right? So the listener is going to hear something louder. They will perceive a louder sound than they would hear with the direct sound. So if you can get that reflection to happen within that 5 to 30 millisecond window, it sounds louder. And when you are in a room where that's happening, and you're like, wow, that person is talking really far away from me, but they sound louder than I would expect them to sound given how far away they are. That's what's happening, is you are hearing their direct sound from their voice, but then you are also hearing their voice reflected off of walls that's arriving at your ears within that 5 to 30 millisecond window, and everything sounds louder. So when we say a room has good acoustics, that's usually what we're talking about. It means it's not that the sound doesn't get quieter the way it normally does. It's that we're using the reflections to our advantage. Yeah?
Would I be correct in saying that it wouldn't be double because some of that reflection would have been absorbed?
Well, yeah, right. So the effect is kind of dependent on how much quieter that reflected sound is, right? So yeah, ideally this would be a really reflective surface, right? It would hopefully not absorb very much energy. And if it's between 5 and 30 milliseconds of difference, it probably hasn't decayed a whole lot relative to the direct sound because it has to be at least double the distance in order to be a 6 dB difference. Right? So yes, there's a few other variables in there, right? You got to make sure that not a whole lot's getting absorbed at the surface, and you got to make sure that the time is narrow enough and that the distance is such. And then yeah, you get a good reinforcement. Well, guess what? Here's the other cool thing. So let's say that R1, reflection 1, hits the listener at 20 milliseconds after the direct sound. And then R2, let's say that hits the listener 30 milliseconds after the direct sound. Well, normally that would be an echo, right? You'd hear that twice. Except that you don't. Because what was the last thing the listener heard before it heard that second reflection? Heard the first one. And there's only 10 milliseconds of difference between the first reflection and the second reflection. Therefore, it doesn't echo. So now this listener hears the sound 3 times, doesn't perceive an echo, and the whole thing sounds louder. And then you got your third reflection. Let's say that is 40 milliseconds after the direct sound. Well, that's still only 10 milliseconds between the last thing that the listener heard. So this one hits you, you don't hear an echo, everything sounds louder. Let's say that R4 is 46 milliseconds after the direct sound. Same thing, right? Still within 5 to 30 milliseconds of the last thing they heard. Therefore, it all goes together. Now, let's say R5 is 55 milliseconds. That's only 9 milliseconds between the last thing they heard. So now they're hearing the sound a total of 6 times, and none of those arrivals is far enough apart that you would hear an echo. And they are far enough apart that you don't hear comb filtering, and therefore you hear it 6 times. And they all sum together. That's a huge lift in level. If you can take that sound and hear it 6 times, that's a heck of a lot more than a 6 dB difference, right? If you can get the distances just right. Yeah.
Would that not make it sound weird if you heard the same thing over 55 milliseconds?
No. That's the whole point, is that as long as each thing you hear isn't more than 30 milliseconds apart, you perceive them all as one thing.
Well, I guess like I'm having a hard time understanding how if the difference between the first and the last one is 55 milliseconds, it wouldn't, even though it sounds like one continuous thing, if the like really long one continuous thing doesn't sound weird, like saying hey
So,
instead of hey.
no, it doesn't. And this is why, because everything you have ever heard in your entire life, you have heard more than once. You have never in your life heard only a direct sound. Everything you've ever heard has also bounced off of something and then hit you, okay? So since the day you were born, you have been hearing this happen. And so you had to figure out a way to make sense out of that. Otherwise, you would go insane if everything in your life that you heard just sounded like a complete disaster, right? We couldn't communicate with each other, music wouldn't work, nothing would work, right? Because it would just be a mess. So what's happened? Our ear-brain system has evolved to the point where we don't notice it anymore. We've just figured out a way to fix it. Because if we allowed it to sound weird, then we couldn't function. So we've just figured out a way for it to not sound weird to us. We've just changed the way we process the information. So it's just a blind spot. It's a blind spot in your hearing that has developed that way. Yeah.
So, again, back to the warehouse. When you clap, it's about like a 4 to 5 second decay.
Mm-hmm.
Clap. But you don't hear your clap twice. Is it just doing this just over and over and
Yeah.
over for 5 seconds?
Yeah, because in that case, the reflections are so close together, and there are so many of them that you don't hear echoes, but it also doesn't go away because it just keeps propagating and keeps reflecting. So here's what happens next, okay? So here's an example of what's happening in a room. So the solid dots are direct sound, and the hollow dots are reflected sound, okay? Eventually, as you get a certain distance away, where would you say, how far away from the loudspeaker do we get before we have just as many hollow dots as we have solid dots? Tell me when to stop. Right about there? Okay. So at that point, if you were standing there, the direct sound and the reflected sound are the same level. Okay? Same loudness. Anywhere past this, the reflected sound is louder than the direct sound. That's what's happening in your warehouse. That is called the critical distance. The critical distance is the point in which in the room, when you get a certain distance away from the thing making the sound, when you get to the point where the reflected sound is the same level as the direct sound, you're going to have a really, really hard time understanding anything. Because most of what you're hearing is reflected sound. And it's reflected sound that's usually coming so close together that it sounds like reverb. You're not able to process individual arrivals like we could in the previous slide. So it just sounds like a mess, right? It's a big, long sound that is louder than the direct sound. Yeah?
In the other picture you had with the listener, that's in a real world, there'd be groups,
Yeah.
rows of people.
Yeah.
So would they hear the same thing as that?
Yeah, depending on where the listener is, what they hear is going to be different, right? The makeup of those early reflections is going to be different, right?
It's going to stay consistent in being, they
Not,
won't be able to.
not necessarily.
Really?
Yeah. We went and measured a church last year where if you were in the front row, you couldn't understand anything. But if you were sitting in the back half of the church, it was fine. Why? Because the reflection off the back wall was so strong that when you were sitting in the back half of the theater, that reflection was coming close enough together that you didn't perceive the echo. But when you were sitting in the front row, that time between the direct sound and that reflected sound was wide enough that you heard it double. Yeah?
So in the previous picture, you had, kind of going off of what you said, you have one person sitting there, and
Yeah.
there are certain reflections that are hitting them.
Yeah.
If you were sitting, say, like 10 rows in front of that person, would the reflections be, like the angles of the reflections be different?
Yeah.
Okay.
Yep.
So it wouldn't be the same.
You got to figure this out for every seating spot, right? Okay. So, but this is a really important concept, this critical distance, because once you get to critical distance and onwards, you're not going to understand anything. And they're going to say, I can't hear it. But what they really mean is they can't understand it, because they're hearing, most of what they're hearing is just a reverberant mess. And they're going to tell you, like a director is going to tell you, I can't hear it. And so what's your response going to be? I'm going to turn it up, right? So what happens if I make the loudspeaker louder in this scenario? Is it going to change the combination of solid dots to hollow dots? No. Yep. I just get a louder mess. The hollow dots get louder, and so do the solid dots, right? So turning it up in this scenario is not going to fix the problem. So how could we fix the problem? Yeah. So why would changing the directivity help? Yeah. So you got less of the solid dots hitting the walls, and therefore less things that come off the walls and become hollow dots, right? So that's what this is. So if I put a horn on this loudspeaker and get it more directional, I have less hollow dots because I got less sound hitting the surfaces and then bouncing off. So now where's critical distance? At what point do I have the same number of solid as hollow? Probably right around there. So before, it was around here. So if this was your critical distance, then essentially only the first couple rows of seats get to understand the show. And everybody else sitting behind there doesn't have a chance. But now I went to some directivity, and I got it almost all the way to the back of the room. That's going to make a much better difference than turning it up will. Okay? Can you think of another way to increase the critical distance? Yeah. So if I added another one, where would I put it? So back in this scenario, I'm up here. Where would I put the other one?
Outside of the co-filtering area for that one.
Say again?
Outside the co-filtering area of that one, so they wouldn't co-filter.
Yeah, so you don't want it too close to the first one, right?
At it, where at the red line.
Yeah, basically if I put one here, then I get some more solid dots right here in front of it, right? And then I could put another one here, and I get some more solid dots, right?
Is that what you would assume that the goal of the people who designed the theater at Kingsman's is not the one? Because that's the system.
Oh yeah, basically that's what they were doing. Yeah.
Because they're usually doing like conference rooms.
Yeah, that's what they were doing.
Sound good.
It wasn't a bad idea. It just
Wasn't
wasn't necessarily appropriate for theater, because in theater we want to make it sound like it's coming from the stage, right? So yeah, that's one way of doing it. You could add some more speakers. This is how a lot of old cathedrals do this. So you got these big reverberant cathedrals because they sound so great for when people sing, when the organ plays, but someone talks and you're just screwed, okay? And a lot of times what they'll do is they'll actually put little tiny loudspeakers on the backs of every row of seats so that you always have wherever you're sitting, you've got a little loudspeaker right there in front of you, and so you're getting tons of direct sound that isn't reflecting off of anything. So you can make the critical distance theoretically be forever away. Yeah, but it looks nice. The Pretty Committee approves because you don't see the big stacks of speakers anymore because they're hidden inside the backs of the.
they're not ridiculously expensive. But yeah, that's.
But times 1,000, then yeah.
500 of them for the same amount of price you would spend on the lighter. So
Anybody think of anything else we could do to increase critical distance besides adding loudspeakers? Anything else? Think like an acoustician for a moment. If you're an acoustician who doesn't have loudspeakers, change the walls. Very good. So, if I'm an acoustician, I don't know anything about loudspeakers, and I don't know that you can put horns on them and keep the sound off the walls. All I know how to do is change the walls, then yeah, I could change the walls, right? I could put up panels like this. I could put absorptive panels all the way across here and all the way across here.
Why move the speakers closer when we just tear down all the walls?
Yeah. Well, or just cover the walls, right? Cover the walls with something, and so you got less sound bouncing off the wall, right? Because a lot of it gets absorbed. You'd increase critical distance. Definitely you would. Okay? But understand that doing that, you got to be very careful because what you want to get rid of are the reflections that are turning into reverberation. But you don't want to get rid of the early reflections because the early reflections are good. Creating early reflections can increase critical distance. If you could get a good reflection that would bounce off one of these walls and hit the listeners within that window where it's helpful, that would help your critical distance as well. And so you don't want to lose that, right? You don't want to lose those bad reflections. So this is why acousticians get paid the big bucks, is because they know where to put the panels in such a way to get rid of the reverberant reflections without getting rid of the early reflections. Because if you can do both those things, you could demand a very big paycheck. I can make the bad sound go away and keep the good sound.
But for the early reflections that you said that it's a good thing, isn't that for like that one row?
Yeah, so you got to figure it out for where everybody sits. Can you angle a wall in such a way that it becomes a good early reflection for everybody? If you could figure that out, boy, somebody would pay you a lot of money for that.
Acoustics supposed to be in it, like during the design process, not really after it's been built as much.
Yeah, it's a lot easier to solve these problems before you build the building,
That was
right?
the big issue with the church was that it was,
They had already built the building.
it was like 300 feet wide and 60
Yeah.
feet deep.
They couldn't change the building, so they just... So what we advised them to do was, all right, you can't change the room, but we were able to find the one reflection that was causing them the most trouble, right? It's like, okay, the sound is bouncing off this wall in particular in a way that is really bad. So if you could make that wall go away, you can't make it go away in reality, but could you make it go away acoustically, then that might help you, right? You could cover that up with tiles like this and reduce the intensity of that reflection. Okay, that's it. I'm out of slides. So,
covered like 5% of the wall with these panels. It was there.
all right, so that's it. That's my acoustics conversation.
Nice. That was very good money.
So how do you respond to people who ask you to do, like, fix acoustic problems? Like,
I say hire an acoustician. I am not an acoustician.
because you said, like, you have to answer it carefully
Yeah.
to
Or-
not piss people off.
Just be honest.
I just say, look, I mean, if it's something I can help with, I mean, if I realize that I do understand enough about what's going on that I can give them good advice with some confidence, then I will. But if I'm not sure and I don't have the time to really figure it out, I'm just going to say, you know what? I'm with you. Like, this is not working. But whatever's happening is more complicated than I can even understand, and you really should probably get somebody who is, I make stuff louder, right?
All letter.
That's all I do is make stuff louder. So I think what you need to do is make some stuff quieter, and that's way outside of my expertise. I wasn't trained in making stuff quieter. I was trained in making stuff louder, right? So there's nothing wrong with saying that. And so when I say you got to be really careful, it's be careful about what advice you give people. Don't give people advice that you're not qualified to give them, because then they're going to be angry at you when they do what you said and it didn't solve the problem, especially if it cost them a lot of money to do what you said. Okay?
That could looks funky. I just cut it off.
Yeah.
Cut off your target.
Exactly. Yeah. It's like that. You just got to be really, really careful about that. Okay. All right. That's it. So on Friday we're going to look at your project. Yeah. Isn't that what I said? Yeah.